Okay, let's get started. So our second speaker, who is also a Frontier Science Award winner, Dr. KJ Li, Dr. Kejia Li, from a professor at the Kafei Institute, Peking University. And however, he cannot make it today because due to emergent family issues. So his previous PhD student, Xu Heng, who already graduated from PKU, now a postdoc at National Astronomical Observatory, Chinese Academy of Science, is going to give this talk on behalf of KJ. So the title of the talk is Searching for Gravitational Wave with the Chinese Pulsar Timing Array Data Release 1. So please, go ahead.
Okay, thank you, Dana, for very nice introduction. Hello, everyone. My name is Heng. I'm very happy to be here today to give the talk on the results of searching for gravitational wave background using the Chinese Pulsar Timing Array Data Release 1, and mainly help KJ to give this talk, and also on behalf of the whole Chinese Pulsar Timing Array collaboration. And I also want to explain this our CPTA logo here. The basic idea of this logo is that we rotate the four letters of CPTA one by one, and to comprise this logo looks like a radio telescope pointing at the up direction. And this logo is also very similar to the Asian character of China. So that is very good logo one. And before talking about CPTA, I also want to highlight the great achievements last year we have done with four collaborations together from EPTA, INPTA, and PPTA, and LiDAR, and also with CPTA. The basic thing that I think that is that we use basically different telescopes, receivers, and different pulsars, and different pipelines, and different algorithms, and also different softwares. We all have very consistent results. This is a very strong evidence for the Hellings correlation curve, which is expected from the 9 Hz gravitational wave background. And I also want to thank Professor Liu Tao, Yan Junguo, and Andrew Zik for giving very nice introductions on the background of pulsar science and the pulsar timing arrays, and as well as 9 Hz gravitational waves. So I can focus on the CPTA itself. And today I'll mainly cover this several contents. First, I want to introduce the history about Chinese Pulsar Timing Array. Actually, the history, I think, of CPTA is somehow very long, because at 2003, Professor Wang Sheguang proposed to build a 15-meter radio telescope at Miyun to dedicate to do pulsar timing array stuff. But finally, that telescope was not used to do that. And in 2017, we have our first CPTA meeting. Even CPTA was formally formed. However, at that time, we didn't get a very good agreement that whether or not we will have the CPTA collaboration. And 2 years later, with fast commissioning, we are able to do some experimental pulsar timing observation using FAST, and the initial results are very, very good, and that gives us a great confidence to do pulsar timing to detect gravitational waves and form the CPTA. And several months later, at Xi'an, we had the second CPTA meeting, and we all agreed to form the CPTA collaboration. And the CPTA basically aims at directly detecting 9 Hz gravitational waves using radio telescopes within China. And at the same year, CPTA project also becomes one of the five key projects of FAST. And so that means that we do not have to write proposal every year to get FAST time. That is great. That is a great help for us. And all I want to say is that CPTA, compared with other PTAs, we are a very young collaboration in this community. And we have a very relatively small core team for for the data reduction and the gravitational wave searching, mainly including some PhD students and postdocs at several institutes within China and universities in China, and also Nicholas in Greece, and Yanjun was in Max Planck. And this team was led by KJ, and actually he's now in Kunming. And we now only use fast to do the pulsar timing, since China now only has such large telescope that can do high precision pulsar timing, and this means that we will have very large shortage of observation time. But however, we have a very high sensitivity compared with other PTAs. And before going to the results of gravitational wave searching, I think I want to talk about some details on the data reduction to make you believe that although the CPTA data is quite short, but we are doing robust research. So let's begin with CPTA observation and the dataset. And we basically, as I said, we use FAST to do pulsar timing. And FAST is an excellent telescope, single-disk telescope that has a very large telescope gain. This FAST is about 3 or 4 times more sensitive than Arecibo, so that is great. And we currently use the L-band receiver from 1 GHz to 1.5 GHz. However, we still do not have the coherent dispersion backend, so now you only use incoherent dispersion. And in data release 1, there are about 57 pulsars. Among them, 40 are in baryon systems, and the remaining others are solitary pulsars. And the data release 1 started from April 2019 and ended at 2022 September. So the data length is only about 3.4 years. That's quite short compared with other PTAs. And in the right figure, I shows how the data looks like. Each dot represents the observation of each pulsar at that day. So that's basically what the data looks like. And you could see that there are some pulsars add later, and some pulsars have less data, and the sampling is somehow less frequently due to the shortage of the total observation time. And here I give you a summary of the timing residual. This is what the final average, the timing residual looks like. And for summary of the timing precision, we basically have 35 pulsars that can be timed to timing precision of about 100 nanoseconds. And in total, we have about 50 pulsars that can be timed to 2 nanoseconds. That is extremely good for pulsar timing. And for the timing precision is quite good because compared with other telescopes, we have for different pulsars, the timing precision can be 4 to 15 times better than other telescope do. So because we have such an excellent timing precision, that gives us very great confidence that we can make a great detection of the gravitational waves. So why is that? Because there was a work done in 2005. That work shows that if we want to detect the gravitational waves, we have to observe about 20 millisecond pulsars with timing precision of about 100 nanoseconds for about 5 years. So now we have more than 20 pulsars with 100 nanosecond precision. And at the end of 2019, we made a prediction when we can make a detection of gravitational waves. And here are some examples. This is the optimistic case. We predict that we can get some results within 5 years. And if we were lucky, we can make some good results in about 3 or 4 years. And in 2022, we decided to freeze the data and we attempt to search for gravitational waves. And the next session, I will talk about what we have done for our data reduction and the noise analysis to make you believe that we are really do great timing. The first thing is that the first thing to do pulsar timing, you got to have a very good polarimetry calibration, because pulsar signals are highly polarized. However, the reception systems in all telescopes are not ideal. So we need to correct this imperfection of the observational systems. However, in fast, because the fade is very good, so the leakage is quite low. So it's very easy to do polarization calibration at fast. Here I show you an example how fantastic data it is. In the left two figures, and the fast is also sensitive, so we can recover very faint. We can also able to recover the polarizations, like linear circular polarizations for very faint pulsars, compared with the slightly smaller radio telescopes, as you could see here. Since fast is sensitive, so we have basically gained the very high quality polarimetric data. With that, we can do some other things. We basically collaborate with Professor Liu Tao to probe the ultralight dark matter using pulsar polarization array, and we are still working on that. But however, there is very large systematic error caused by the anospheric correction. There can be very large systematic error, so we are still looking into that to see how the systematic error look like. And a second thing that can affect the pulsar timing is the so-called scintillation effect in pulsar observations. Scintillation phenomenon is just everywhere in pulsar observation that can change the pulsar shape or the pulsar brightness in the data. So we look into the scintillation in the data, and we measure the scintillation parameters and the scintillation arcs in all the data, and we try to find the correlation between timing and the scintillation parameters. And basically, we found there's no clear correlation between timing and correlation. So we can ignore this effect in the later timing analysis part. And the third thing is that if we want to compare the timing data with other PTAs or other telescopes, the easiest thing to do that is you can compare the timing parameters of each pulsar from CPTA data with other PTA data or other things of measurement. So here we measure the astrometric parameters of each pulsar, and we compare these values with previous published values, either from timing measurements or VLBI techniques. We basically found that both of these results are consistent. So the timing basically are reliable. And we also try to measure the post-Keplerian parameters as well as the binary parameters. We can basically compare them with other works. And the result is that all these measurements are basically compatible. So by comparing the astrometric parameter and the binary parameters, you can see that the timing data, the pulsar timing is working just fine at fast. And the timing data collected with fast is very fantastic is very fantastic. So we can believe them. And the next thing before we conduct the gravitational wave search is that we need to do the noise analysis of single pulsars. So we do very robust timing noise analysis works on the single pulsars. We use 4 different pipelines to do such noise analysis. Basically, we got very consistent results on the white noise, the DM noise, and the red noise between these 4 different pipelines. So we can see that our noise analysis is also very okay. And here I want to see that we also use 42++, that is written in C++, to do the following gravitational wave searches. So here this just means that this pipeline worked well. And we also do some comparison works in CPTA and other PTAs. We compared the noise parameters in the noise modeling and compared them with other PTAs. For all these pulsars, basically the the noise parameters are just consistent between different PTAs, although there may be some slightly larger differences that may be because we only plot the error bars, but actually there should be some 2D contours. If you compare the 2D contours, they are more or less consistent. And this may be also another reason is that because the CPTA data is more recently collected, and for other PTAs the data collected more older, so there may be other non-stationary process in the noise processes behind the pulsars. But basically the noise analysis results between PTAs are consistent. And to understand what happens for this white noise parameters, we also do the jitter noise in the time domain. We measure the jitter noise in time domain in each pulsars, and then compare the jitter noise with so-called white noise parameter equal and equal. And we found that the jitter noise agrees well with the equal parameter. However, the equal parameter seems like to be originated from the instrument. So we can basically understand what the white noise parameters comes from. And this is a very good agreement for the timing and the noise process and the results from noise process. And this is agreement between two different ways. And another thing that we can do using the timing data is that we can use the pulsar timing data to test the solar ephemeris. We just use the timing data to check the difference between the different solar system ephemeris, and we found that those have some between this solar ephemeris there are some systematic difference such as rotation or squeeze or twister between this ephemeris. And the next section, I will talk about what the results we have got from gravitational wave searching. Just like other PTAs do, we basically search for the common rate signals in the timing data using the CPTA DR1. We just assume a power law spectrum like everyone do, and we infer the spectral index and the amplitude of this common noise process using in the Bayesian framework. And this figure shows how the results looks like. We do see some signals because we do see there are some signal in the amplitude. However, the constraints on the spectral index is somehow very loose. This is because the first reason is that our data is quite short compared with other PTAs. That is only 1/4 or 1/5, 1/4 or 1/5 of other PTAs. And the second reason is that we didn't marginalize. Oh, sorry, we didn't. Sorry, here is we didn't marginalize the white noise in the gravitational wave analysis like other PTAs. So there are more parameters in the Bayesian analysis. So our constraints on the spectrum are quite loose compared with other PTAs. However, these are basically consistent. And the second thing that besides of searching for the common noise process, we try to search for the spatial correlation caused by the GWB. That is, we search for the Hellings and Downs correlation curve. Which is the key thing that the key evidence for the gravitational wave background. And finally, we found evidence for such a correlation with 4.6 sigma at 14 nanohertz. Basically, we did this in the discrete frequency. And here to verify our results, we also did two simulations. In one simulation, we didn't we didn't inject any gravitational wave signal, and using the same detection pipeline of the gravitational waves, we didn't detect any gravitational wave signal. And in the comparison group simulation, we injected a very strong gravitational wave signal in the data and in the similar data, and then we run the same pipeline, and we got very strong detection of the injected gravitational wave signal. What we did here is that we basically, what our pipeline is basically detect such signal in discrete frequency. The reason is that we can constrain the spectrum very well. Basically, basically what other PTA do is that they just assume the Apollo spectrum of the underlying GWB and then do the HD curve searching. However, we can't do that because if you assume the power law spectrum and then search the HD curve like other PTAs, you get lost in. And the reason why we do that at the frequency being around the 14 nanohertz, which is not the lowest frequency being, is that if you do some theoretical calculation, you will find that when you calculating the correlation between pulsar pairs, you'll find that the systematic error of the correlation is very large at lowest frequency, and this systematic error will decreases as the frequency increases. So you would better to search that in higher frequency. However, you can't go too high, frequency that is too high because the underlying spectrum is power law. So the signal here at high frequency is much lower than that in the lower frequency range. And here you can see that we did in the right figures. The left three, I showed the detection results with three group of data. One is real data and two are similar data at the lowest frequency, then the 1.5 times of the lowest frequency and the 2 times of the lowest frequency. You can see that you will get a better result at the 1.5 of the lowest frequency, and at 2 times of the lowest frequency, the detection signal to noise ratio is somehow much lower than what you get in the middle pylon. And as a hindsight, you may wonder why we could get such a detection. I think we are somehow very lucky. Here I borrowed the results from other PTAs last year, and I put them all together. There's the free spectrum of the underlying GWB. You could see that the polar spectrum is very obvious. However, at a frequency range about from 10 to 20 nanohertz range, you could see that there is a very obvious bump top of this polar spectrum. So I think that's why we are lucky here to get some very interesting results only in this single frequency beam. And we also note that we can also fit our results using the dipole correlation and get a single to noise ratio of 4.1 sigma at the same frequency beam. However, the HD correlation curve is still strongly supported because the base factor of HD correlation over the dipole correlation is about 66. So the HD correlation is more supported. However, we cannot exclude the possibility that the correlation is dipole. And it's possible to use the correlation curve to further test whether this correlation is from other polarizations besides of plus and cross correlation. So you can study the polarization of gravitational waves, and you can also use the correlation to test the mass of graviton. However, I think at the current stage of the SNR of current detections of hopeful PTAs is still too low to do these experiments. And I also want to mention that we try to search for the continuous gravitational waves from single sources. And we try to do that, use our basic pulsar, try to search such gravitational waves. However, we didn't get any detection, and here we only set upper limit for all sky, and also we get some average upper limits over the whole sky. And we are basically working on blend search of single continuous gravitational waves and targeted searches from other surveys, and this is underworking. And the last two parts, I want to give you some predictions and expectations of the near future. The first part, the first thing is that we got new data sets because compared with DR2, now we basically have nearly 2 years new data. Here the data within the rectangular is the CPTA DR1, and we have, compared with DR1, we have even more pulsars, and we have more data. So you can imagine that we could have more gravitational wave power within our data, and where we have more pulsar pairs, so you can expect more higher beta sensitivity. However, in this longer data, the timing noise and the DM is also becomes much more complicated. So we are still working on that. But the live result is that we use the longer data set, we can got very much better timing results. You can measure many more parameters, and you can measure the pulsar distances much more precisely. And the pulsar distance is very important for later continuous wave searching. And we have did some noise analysis for single pulsars to the new data set, and it shows that compared with DR1, with the new data set, we can constrain the noise parameters much better than DR1. That is good news for the future noise analysis, since because in DR1, basically there are still some covariance between some timing parameters with the noise modeling. So that will be much better in the new data set. And for the infrastructure side, we are basically building new telescopes, and there will be two very large radio telescopes within China. One in Xinjiang Qitai. This is one. This is a 110-meter fully stable and full-band radio telescope, and this telescope is already in construction, and I think this should be done before 2030. And the last one in Yunnan Jingdong, that is quite southern. So we can with these two telescopes we can access much more radio pulsars in the southern sky. So that is quite good. And the Jingdong radio telescope, I think the contract is signed. However, we are still working for a green light, but I think the good news is coming. And with these two radio telescopes, we can increase the pulse numbers. We can increase the numbers of pulsars for a lot, and increase the frequency coverage, and better for removing the effect of interstellar media. And we are upgrading the low frequency array called 21 centimeter array. This array was originally built for detecting hydrogen ions from high redshift to study the realization. Basically, we within the SK Low pilot project, we are upgrading it to make it capable of observing and timing pulsars. And this year, we have basically used some of its subarrays to observe pulsars. Here is an example. So I think we can make some great results with the new upgraded 21 centimeter array in the near future. And with this new facilities, including one large radio telescope and this array telescope operating at a very low frequency, we will increase the pulsar number and increase the data volume, and also the frequency coverage that can be used to better remove the DM noise in our data. So to increase our sensitivities on gravitational waves much more. So as a brief conclusion, with our short data cube CPTA DR1, we had some very strong evidence for the gravitational wave background, and we are working on the new dataset that I think will give us many more exciting results. And we are also working on building new facilities, including telescopes and upgrading array. And finally, I want to thank the ICBS to recognize our work. And I think compared with the engine, I hope that we can have 6 sigma results in the next years. And also I think there's a very bright future for both FTA collaboration and the CPTA. And I will stop here. And thank you. Yeah.
Thank you, Heng, for the nice talk. So the dipole and so on, and this interesting effect. You mentioned somewhere you were running BaseFM, but that's still in progress. So do you see any constrained ephemeris term which might be causing this apparent dipole correlation?
Actually, I don't know. Actually, I don't think ephemeris is a very important. I don't think ephemeris is a very important effect in timing in the search for GWB now as we see in other PTAs. However, I think much more important fact is solar wind. I think at current stage, all of us didn't take care of that effect very carefully. I think that is more important effect that we should take care of in the later analysis. Yeah.
So are you implying I mean, what did you do to take care of the solar wind in your current work? Did you just use the tempo 2 timing model, or did you include
I think we will include that in the noise analysis.
Yeah.
Incorporate it into the final GWB search.
A little detailed question on the Hellings dance curve fitting plot. So I want, yeah, this one may do it. Yeah, for the middle panel, the 180-degree data, it seems lies quite below the theoretical curve. Is there any explanation for this?
I think that this is just about 1.2 sigma. I think because I think for all of at the degrees of 180 degrees, there are two small number of pulsar pairs. So there will be very large systematic errors, I think. But I'm not sure. I'm not very clear that all of us have such a large systematic errors. Yeah, I think here all of us just have two small number of pulsar pairs, but here I don't think there is large systematic error. I think it's just within an error bar. Yeah. Yeah.
Okay, thank you.
Yeah. Yeah. Because they just have different, when they said, yeah, they have different samples because for EPA, the telescopes are rather northern, and for PARCS, it's very south. So PARCS mainly observe southern pulsars, and EPA just observe many northern pulsars and some some thousand pulsars, so the distribution of final pulsar pairs is very different. Yeah. And because I think because for PPTA most of the pulsars are concentrated in the galactic plane, I think. So you will see that the pulsar pairs at large separation is relatively small. And for EPTA, many of the pulsars are more northern, and so the pulsars are more distributed. So the pulsar pairs at the large angular separation is more than PPTA. So this also happens for the Meerkat PTA, I think. For the Meerkat PTA, they also have the basically the most pulsars are in the galactic plane. So yeah.
Saying the new IPTA result will come up soon.
Yeah, should be quick.
Yes, we're working hard on it. It's a big job. Well, in theory, you just add those two distributions, and that gives us our total sky distribution, because we will have pulsars in the south and the north hemisphere of the sky. So it'll become much more uniform.
Yes, a relevant question. I was going to ask is whether you're going to use something like cross-validation to separate your entire sample into different sets and to see whether you actually obtain the same result from this cross-validation test.
Yeah, I think we should do that. I think we should do that, but we should do that. I think that's a good idea.
One way of cross-validating is to divide your data set into two and check you get consistent results in time. When we did that, as you saw, we get an upper limit in one set and then detection in the other. So the hope is that if we divide spatially, we get the same answer. But things are interesting.
Yeah, and another experiment I think a lot of people had done, maybe Sven will not mention, is that they remove the pulsar one by one to check whether the result is consistent with the expectation. Yeah, I think there are many cross checks that you could do, but I think that is too time consuming. Yeah, because such Bayesian analysis spend too much time.
Any more questions? Okay, if no more questions, let's thank Heng again for the
Okay, thank
very
you.
nice talk. Thank you.
Thank you.